So today, as she mentioned, I've been a structural engineer for a long time, since 1995. Okay, thank you. And so, in terms of how fast technology has changed, when I first started, we didn't have computers at our office. We had 3 computers for the entire office. So, how we worked was very manual. And then about a year in, maybe 96 or 97, I don't remember, we got our computers, and if everyone remembers, we got Excel. And Excel changed the game for structural engineers or all engineers. Instead of doing one calculation at a time or on a calculation pad, we can do it in Excel. We can do 100 in a few minutes. So I see AI as being the next generation of Excel, but much, much smarter. And so today I'm going to be talking about AI, and personally, I think AI is a terrible term. Artificial intelligence. It should be called embedded intelligence, and I'll get into that shortly. So this image that you see here, I created using a software called DALL-E, which is part of ChatGPT, in about 30 seconds. All I said was I wanted an image of structural engineers in the future using AI in the form of Tony Stark, if you guys see that movie, right? And that's how I see AI being used for engineering, is that it's a sort of an engineer with superpowers, if you will. So today I'm going to go through all of these things. I'm going to go fast. I'm based in New York, so I'm used to speaking fast. But if anyone has any questions, I'll be glad to answer questions after. Many of you know Thornton-Tomasetti. We're a large engineering firm. We have a large office here in Mumbai and Pune and Chennai, which is why I'm here this week. And as she mentioned, I run a group that does a lot of computational modeling, software development, AI, and R&D. And our journey of artificial intelligence actually started in 2015. One of my developers told me what machine learning was. And if you recall, the big technology companies like Google were talking about big data. And I didn't know what that meant, but when he explained to me what machine learning was, which was essentially taking a bunch of solved solutions by people in our office or smart people in our office, you fit a curve through it using statistics and math, and then sooner or later, all you need to do is ask that application, which we call machine learning models, that question, and it'll give you the answer. So it's very much what people do. So over a long, long career, 20 years plus, you can ask someone a question about a beam or a column or a shear wall or a truss, and they'll give you an answer instantaneously. What if you can take all of those answers, store it in an application, and have it accessible by the entirety of the firm? That's the promise. Some of our applications now are utilizing commercial software. One is called TestFit, one is called Schema, which I'll show. So what we've done over the years is we learned a lot, and we've shortened the schedule from training a model, let's say a beam or a column, from months, literally, to days. And so that's the difference. And we can take those models, those applications, and give them to the rest of the office. So why should AI be, engineers should be aware of it, and not just aware, but very fluent at it. This is, because we're all engineers, I like to refer everything to Excel. So I call it the Excel to the power 10. And sort of machine learning, artificial intelligence giant at Stanford and Google, he calls it the new electricity. And the reason why he calls it the new electricity, Andrew Ng, that is because it's so widespread. When you do your email and it starts to predict the next couple lines, that's AI. Even in PowerPoint, there's AI. Amazon, Google, Facebook, all of the big technology companies in the world are using AI. In fact, they wouldn't be in business without AI. So these are some references that I found. They're good references from Harvard Business Review, as well as McKinsey, showing the firms that start to utilize AI in their practice will accelerate their growth and their profit margins in the next, 10 years or so. And the ones that don't may perish. This is where I see where we are in Thornton-Tomasetti. We've done all this research over the years. We have a very good understanding what AI can and can't do. Obviously, it changes every day, seemingly. But what we know it can do, it can extremely accelerate what we do at our company. So it also solves a lot of problems in our industry. There is a talent shortage, particularly in the United States. Actually, there was just an article yesterday in Newsweek about the shortage of engineers in the United States is going to significantly impact projects, bottom line. And we actually, if we didn't have this, our office here in Mumbai, I don't know what we would do, to be honest, with the lack of engineers and that are getting trained in our office in the United States. All of you know that, particularly working with, very design-oriented architects, there's a lot of, and owners as well, there's a lot of iteration in projects. And so therefore, we need the tools that get us through those early phases of design quickly. And machine learning can do that. There's a steep learning curve in engineering. The way I learned was to spend 5 or 10 years doing something over and over and over again, and after 5 or 10 years, I started getting good at it. But we don't have the time these days to train our engineers in that time period. So there needs to be a better way of accelerating their growth and their learning, and I think AI can actually do that. And I also think, so you saw, we have 50 odd offices around the world. It is technically not feasible for every engineer to have access to the smartest people about a particular topic. So how can we again, using that term, embed intelligence into an application such that every engineer has access to the smartest engineer in the office? Now, that's not going to happen at the entirety of scale of what an engineer knows, but even if it's the simple aspect, I call it simple, but the learned aspects of engineering, that's very powerful for an office. It's a shortcut to the answer, so we're not reinventing the wheel. So this is a simple answer. I used to be a carpenter in high school and college. There is no way I can compete with someone with the nail gun versus my hammer, doing one at a time. So this is a statement from the CEO of NVIDIA, Jensen Huang, who says that while some worry that AI may take their jobs, someone who's an expert in AI will. And I think that's very true. He's growing his company at ridiculous speed, and there's no end in sight. This is my statement, having been an engineer for over 30 years now. It is the most impactful technology that will transform, and the reason why I say that, it's not just technical aspects, it's also marketing, it's going to also impact finance, human resources and recruiting. It's going to be spread throughout the entirety of the business of engineering. So I want to show you some applications. And again, as I mentioned, at the crux of machine learning is data and data science, which is the part that trains the model. That's the artificial part, by the way. But the actual data, the solved solutions are real. So if you can fit a very nice curve through a series of data, and then sooner or later you ask that data a question, it gives you an answer from those solved solutions, that becomes very powerful. So these are just the types of machine learning we've been doing and researching in our office. But I want to show you some. So this is 2018. We built a software called Asterisk. Asterisk was based on about 3 years of research that we had done. And this designs a full high-rise building with a reasonable accuracy, probably 80 to 85% accuracy, in under a minute. All we needed was the massing of the building and the core dimensions, and it would design the building either concrete or steel using machine learning, all machine learning. The critical aspect of this is that what we wanted to do, and what was very new at the time in 2018, was something called qualitative analysis, or structural optioneering, as we called it. So instead of doing one design or two designs and then saying, okay, I'm going to take the best aspects of each, we can do 20 designs in a matter of hours, and then do a comparison of those 20 options to then optimize, if you will, that particular design and move on. This example, what you see here is a building that we designed called 10 Hudson Yards in New York City. And in fact, the machine learning did show that concrete was the cheaper option, and that's the option that they actually used. Now, we did this study after it was designed, but it just demonstrated that this type of technology could be used and should be used in the future of engineering. Fast forward a few years after that, our machine learning model for concrete columns is embedded in a commercial software called TestFit. So this is a parking garage module that, as they're moving around the parking spaces and the dimensions of the columns and the number of floors, the columns are changing instantaneously. And I've checked those myself, so I know they're right. So this is our latest truss designer. What this is doing is we actually built an FEA solver that is doing a structural analysis to calculating the forces, but then pointing those forces to our trained models that design steel members and instantaneously resizing the members based on the geometry of that particular truss. Now, an engineer can do a truss like this in maybe a few hours if they're very good. This is doing it in a few seconds. And we can change we can change the type of members with W10s, W14s, double angles, various geometric options. And this is near real time that you're seeing here in this video. And so we've gotten the validation of these we do with commercial software. This is SAP 2000 and CSI product, and we're within 5%. And for those early phase of design, within 5% is absolutely, totally fine. We also do more conventional methods. This is called confusion matrix analysis of what the tool predicts versus what the answer actually is. And when you see these very clean 45-degree angle, that means the answers are almost always predicting what the data set we had. This is a design that I did in 1997, or 98, I think it was, using 2D methods. It's in Miami, Florida. And it took me to design this truss a long, long time, I can tell you that. 372-foot span truss. We pointed that same analysis that what we did was we're doing an FEA in the background, calling our machine learning model for sizing of members, beam column trusses, sizing, and the analysis within 5% of what I predicted, full design at CD level in 1997. So the power is there and the speed is there. This is a ubiquitous concentric brace frame. This is a data set that we generated that both calculates strength, stiffness, and optimizes using virtual work for this concentric brace frame. Each level has a family of member sizes. It's very advanced machine learning. And again, an engineer could do this probably in 8 hours, 6 to 8 hours or so, but we're doing it in minutes. It's never machine learning, by the way, is never 100% right. It'll get you close. But at early design phases, when it's very iterative, that's very powerful. This is office floor steel design that we trained using code-based results, but then fed it into a machine learning model. It understands corner bays versus exterior bays versus interior bays, and has the vibration analysis built into the results for office loading. And we can change the dimensions of those bays, and it instantaneously resizes. And the results are within less than 5% actually to real actual commercial software results. So, full disclosure, we haven't completely rolled this out to the entirety of the firm. We are still testing with sort of the more advanced engineers in the office, because there is an additional aspect of AI that we need to train engineers how to use it and how not to use it. It's because it is not 100% correct. I would also argue that there's no engineering designs that are 100% correct anyway, but that's a different story. So we have now trained timber, steel, and concrete for the majority of structural members, or almost all the structural members of a building, for both gravity and lateral. And as I mentioned, our software is now embedded in this other commercial software called Schema, which is a new startup that does, for now, does residential design. But you will see here how it works. It's very much like our asterisk in 2018. It does a massing. It sort of splits the building up into 2 bedrooms, 3 bedrooms, and studios. It calls our machine learning models and instantiates the members in the building. So this is not meant to give, the designer or the architect or the developer the exact member sizes. It's going to be about the depth of the member, the estimated weight of the structural steel. Again, we have concrete and timber as well if we want, but for now they have steel in there. This is what I'm actually very excited about. So what we've done is, Thornton-Tomasetti had a very vetted plate girder designer, and we took the logic out of the Excel spreadsheet, created millions and millions of results for plate girders, and now all we need to do is give a moment in shear. I fixed it at a design capacity ratio of 0.8, and using generative AI, which is very much the technology behind ChatGPT, is that it's predicting any number of designs that actually work: deep members, shallow members, fat members, and we're post-processing and calculating the weight per foot of the members, as well as, for the engineers out there, the shear flow, so the weld that is required to make those members composite. So I think it was Anand who teed it up for me about AI predicting connections. This is a connection designer that we had using spreadsheets. We took that spreadsheet, created 10 million, how many results, and now we trained a model that all we need to do is pick the shear, pick the member size, pick the bolt type, 3/4, 325, we would use A325 and A490 bolts, all different sizes, and it predicts the number of bolts. So some of you may say, oh, I can use a spreadsheet and do the same thing, and that is absolutely true. The power of AI, of these machine learning models, we can do this for the entire building. And so this next example this is a building I was the engineer of record for in New York City. Actually, it's called the Tata Innovation Center on Roosevelt Island. I took one floor, and we pointed that connection designer at one floor. We have the shears sort of already in the model. And what this example is showing is, if you look down at the bottom, it's calculating the connection weight, the total number of bolts, and the total length of weld for the entire floor. Now, a person can do that one by one, but it would take them a week to do, and we're doing it in seconds. And these are the types of things that fabricators want to know, and now we have a method actually of optimizing those connections before it gets to the fabricator, so as a designer. So this is just a proof of concept, but it shows you the sort of the power of what these models can do. They are not 100% correct, as I mentioned, but from a qualitative analysis of getting a comparison. Now, the other thing you'll notice too is that there's not a lot of parity of shear forces in this model, so you're not going to see that many differences, but it just shows you what it can possibly do. I'm going to show this really quickly, not to get into it too much, but I want to talk about, we have a tool that does embodied carbon calculations. It's an internal tool called Spotlight. We have an open source version called Beacon. Point of it is that, and this is another building that I worked on in New York City. What I did was just to prove to our young engineers that we don't need to build these full crazy 3D models, is I did one bay or two bays of design using machine learning. I did one column or two columns. I did one footing, a couple of footings, just to get a sense of the overall sort of weight of the building. And I've done this before for competitions. This is a project that I worked on. We actually won this project. It's in Maine. It's for the Rue Institute. And these are the key aspects, right, of a building. If we can predict those elements to some reasonable accuracy, you don't need to do a full analysis. And so this is my desire as CTO of the company, is to instill to the young engineers that you don't need to do a full building analysis to sort of give the responses to your clients or to your architects and designers. You need to have enough information to be educated for the framing depth, for the weight of steel, potentially for the cost as well. So what you see here is what the red is what we have machine learning models for. And so I'm going to go through this quickly, but just to show you that what I did, which is the way we used to do it when I first started, actually, because we didn't have the time or the tools to do it. But if we can do these using machine learning, those base studies, column studies, foundation studies, and then aggregate that for the entire building, you can get a fairly accurate design in hours versus days or weeks. So on the left is the model that I showed you. That's the machine learning model previously. On the right is a tool that we created that does actual non-machine learning CD level design. It's within 5%. This is one column designer. You can do corner column, exterior column, interior column, whatever you want to do. I decided to do one. In this case, I did one footing. We have a machine learning tool that actually does wind calculations and seismic. I took those loads and pointed it to our concentric brace frame machine learning model. And then I created this little dummy model in Revit, which is all we need for the prediction of the overall building. And put it into Excel, and I'm getting pretty close. So subtract the 2 PSF. 2 PSF is for the deck itself, not for the structural steel. So a 12 pound per square foot, 10-story, 100,000 square foot building is pretty close to being accurate. So this is, again, instead of spending days and weeks, I can do it in an hour and have a good understanding of that building. And then we have nice graphs to show the embodied carbon and things like that. And the power of this is now you can chain these applications together to create a full building analysis. So what I did one by one by one, I chained it together and put it into a singular application. So it's recalculating wind load, recalculating those column designs, footing designs, brace frames, and aggregating that into a full building analysis. So these are the things that we've been working on. Structural machine learning, predictive AI, computer vision. We have a startup actually that we spun out in 2021 called T2D2.ai. I showed you the generative AI. It's very good at extracting text from documents, sort of a graph, if you will. And that's the data mining aspect. And it's very good at language as well. So these are the things that we're doing. As I mentioned, the biggest aspect, particularly of a mature firm like Thornton-Tomasetti, is that we need to train the engineers how to use it correctly, because it is a new technology. It will require training. It will require people to get a good sense of what it can do or what it can't do. But once they do, it will be, a very accelerated sort of early design tool. I don't want anybody using it for construction documents or anything downstream. It's for those early phases when there's an iterative process going on. Thank you.